Alrighty, I think we are live here. So, welcome to the fifth episode of How Things Work. Before we get started, a quick disclaimer: so this podcast is for informational purposes only. Nothing said on How Things Work should be interpreted as an offer to buy or sell securities, financial advice, legal advice, or as an opinion of the employers of which our guests work. They may hold positions in the companies or projects discussed. Up to you if you want to interpret anything as technical advice. This one, maybe you would, but we'll see where things go from here. So, for our fifth episode, we're going to chat finally about storage and really how to do transaction execution and packing and everything that you really want to think about when it comes to building out the foundation of your execution engine with some incredible folks from the LayerZero side of the world. So before we get started, let's do some quick introductions. So Thomas, you want to start us off?
So my name is Thomas. I work here as a researcher at LayerZero Labs. Super excited today to talk about some of the work we've been doing on storage and execution. So,
cool.
Hi, my name is Isaac. I work as a chief architect in the company, and so we design, build protocols.
Cool. And then Roz, you want to give a quick introduction as well and kind of what what are you guys doing?
So I'm Raz, co-founder and CTO of LayerZero. Fun fact, Thomas and Isaac were actually one of the original people on the early part of the team. Thomas helped work with us with the original white paper and has been here since pretty much the beginning, and Isaac as well was on the early team when we did the first endpoint and had everything out. So they've been with us forever and a really core part of our team. We at LayerZero have built out a research team, which currently I think it's 8 PhDs on the team, even though we have 9 total PhDs. Someone decided to get 2 on the team. And our mission and our vision here is to help push towards a more decentralized ecosystem. Right? We see how things have been going in the space, where it's easier to go a more centralized route to add to scale vertically to meet those needs, right, and to make a better experience. But that comes at the cost of that decentralization part. We think, and we want to make it more accessible. We want that our principles at LayerZero, being permissionless, censorship resistant, and immutable, and we want to help blockchains and other products that are out there move towards that. And so we built out a research team to help. How could we? And our vision is, how do we put out research that makes really decentralized things like, say, Ethereum or anything like that be competitive in terms of experience with the more centralized blockchains and centralized experiences that are out there, right? Where you can have that fast, snappy experience, but still have the properties and uphold the principles that this whole industry was founded on.
Yeah, I mean, my first question was going to be pretty simply, you guys are an interoperability project. You could do a lot less to be an interoperability project, maybe. So, why the hell are you doing all this random research? Well, not random, super interesting, deep research in all these different areas. And I guess it's just because you're interested in it, and like you said, feels like there's a need to level up some of these decentralized projects without really giving up that performance thing, and you feel like there's a gap there. I think that's
Ryan and I we got in this space for the actual tech, for the principle. I know it's people say that, but that's what we're here
first
for.
Time I'm hearing this.
Yeah, we always say that. I think we put our money where our mouth is here, right? With building this research team, right? That doesn't necessarily drive value to LayerZero right now. But we think drives value to the space, which is great for everyone. The boats all rise when the tech gets better, and we think helps shape the future of what we want to see. Right? I want that decentralization. I want those properties, the vision that Bitcoin and Ethereum have. I want that to win. I want it to be truly, in that sense, where governments and other parties can't interfere with transactions going through, that everybody can It's really accessible, and we want to build that, and so we want to see that through, and we have, I say, the best engineering team in space, some of the best researchers. We've been working with external research teams as well. We want to move the space forward, and we care deeply about our work and crypto as a whole.
Well, let's take it from there. Now that we got the stage set a bit on what the goals are here. So, a few months ago, I got a message from Isaac, I think, which was like, "Hey, we're working on this database thing. Like, do you want to take a look at it? Like, seeing you're working on the firewood stuff, you're working on this other stuff. Like, what's up?" And I was like, I mean, database, I'm happy to poke around. And so the quick context there was I had previously been working on a project called Vilmo, which don't hate the naming. I don't have the catchy names that you guys do with QMDB and FAFO and stuff like that. But clearly, obviously the authentication of the database, the Merkleization stuff can become a huge overhead. And what's the simplest database is just using the log and some RAM. Now, what I had figured out was like you could kind of rearrange that log in a certain way to still get efficient sync, but like talk about not being able to prove anything about what's actually in it other than just being able to sync it. And so I was like, well, I guess this is the best you can do. Like, I don't really know how to take it further from this. And so it felt like it just dropped out of nowhere. You basically sent this paper over, and I was like, shit, there is a way to add authentication to like what is a pretty log heavy construction. And so before we get into this, I just wanted to say I'm a huge fan of this, and it totally took my thinking like one step further on like what I thought was possible with a lot of this database technology, and the fact that you guys implemented it and put it out in like an MIT Apache 2 also construction is super awesome for the space. So let's get into that first. So like QMDB, first thing you guys released, why database first? I think people always talk about state, but like I guess you guys thought the same thing first too.
Yeah, so we kind of this research team we pick what we want to work on, and we kind of look, our favorite things are bottlenecks, right? So when we're looking at all there's many, but all the existing bottlenecks that exist to get speed within a blockchain, storage is a major one. So like if you're thinking about sequencers, like for them to hit high for a layer 2 or anything like that, for them to hit high throughput, what ends up happening is the MPT data structure, which is most commonly used, or even like NOMT or MonadDB, they're all kind of following, jazzing up MPT, right? How do we make it more efficient or optimize it for how it writes to disk and everything like that? But in the end, it's just a poor data structure to use in the first place, right? It has the best properties of it is that you can Merkleize it and you verify it. It's a verifiable database, but it is not great for actual disk usage, right? And so we just took the common knowledge. Let's optimize
before you go into it. Is like you said, it's not great for disk usage. So like, what are some of the properties of like a traditional MPT? Maybe before we get into some of this QMDB of like, why is it so bad for disk usage? Because I think you snuck it in there really small, but like
yeah, I mean, there's maybe we can dive deeper, but overall high level is like you are writing all over a trie, right? And a Merkle Patricia trie, right? So anytime you're inserting, wherever it goes is going to be random reads and writes to disk to update it. Where like you hinted at with QMDB, it's a log-based approach. Everything is append only, and then so it gets there's a lot of write amplification with MPT, which is very bad on the disk side. And so the way we thought of things is from first principles. We kind of always just take away whatever is common wisdom or common approach and say, how would you do this from scratch, right? And if the bottleneck is the actual disk itself or the SSD, what things can we do to make that more efficient? And so write amplification is the real problem. And so if we could do a log-based approach where you're appending and writing in chunks, and if we can do it that way, if we can Merkleize each chunk before we write it, right? We can do in-memory Merkleization, which is Merkleization is very expensive on MPT because you need to pull from disk and then re-Merkleize every time you update the tree. And so if we do that, right, and that approach, then we solve that big bottleneck. And so it was from there as to how we make it verifiable. And we can dive into the whole data structure and how it works. But that was the big unlock for us. And then the next steps after that were, we've made this QMDB, and the unlock is that we can do 1 million TPS. Well, of course we have to do that. And so the next step was to go to FAFO. When we did with FAFO, which was, that execution became a problem. So how do we schedule for maximum parallelization so that we can have the execution engine, which can go even faster than the QMDB, now be able to do, way more in parallel and achieve what we could essentially have with FAFO and QMDB in that paper, which we also open sourced the code for, can do, a sequencer can do 1 million TPS. Is the vision there, and so it's just seeing that through.
Can I double click on the disk part a little bit, right?
Yeah.
If you look at the latest available open source, like NOMT, right? And even from the available documentation of MongoDB, right? They're doing a lot of random write. And if you look at the hardware spec, the random read is always faster, like often 10 times faster than the random write. So you don't want your system to be bottlenecked by a much lower spec, which is random write, right? You want it to be bottlenecked by random read, and that's you can find the same consistency of QMDB's performance in terms of like a rewrite throughput.
Yep.
You don't even need to benchmark it. You can just look at the hardware spec. Oh, that's the random read throughput, and that will be the maximum of QMDB. And it's like 99% is the same value or close.
Yeah, I mean, I think when you look at some of these other things too, like people, when you hear log-only database, which is, I think, this is this like core insight we're talking about here. When you change something, that means you typically have to like rewrite to the end rather than rewriting in place. And I think a lot of people think that sounds super inefficient. So like, what is actually going on behind the scenes here where that's actually not that inefficient? In fact, it's maybe more efficient than what is actually going on behind the scenes of some of these databases. Go ahead, Thomas.
You can really see it like typically when people use MPT, they're going to layer an MPT sort of virtual data structure and actually lay it out on disk in some log structured format, like an LST, RocksDB, LevelDB. So, it's pretty clear, I think, at least from a systems perspective, that the log structured data structure is going to be more efficient in practice. But then it's still inefficient because you're layering on this unnecessary MPT sort of on top of that.
Yeah, I mean, I think what people often don't realize, right, is that the like a lot of these things you layer on have their own log in them already. To preserve like unclean shutdown, right? So like whether or not you know it, you already write it to a log. It's just that there's a secondary process that's putting the output of that log in even another place on disk, and then occasionally also rewriting it again during compaction to keep it sorted. So when you think append only or log, you should think it's only actually really a subset of what you are already doing, which is one of the reasons why it can be so efficient. But a lot of these, I mean, I think just to frame even a bit of what other projects have been doing, right, is what if you just use the Merkle structure from like the data you need to prove just as the logical lookup into the disk rather than having these like layers of indirection? Because you mentioned, during this like proving process, right, you may have to pull a bunch of stuff from the tree to actually figure out what the next proof is. But each one of those reads could already be many reads, logical reads on disk, right? So like there's this cascading problem kind of behind the scenes of both read and write amplification. So, I mean, I think, we've talked about all these like different things that it avoids. Well, like, I guess it probably makes sense to go to like, well, how is it designed such that it avoids that, right? That you can still prove things from this log. So maybe it makes sense to go through it from the perspective of you're adding something to the database. What happens?
That's a good point. So do we want to?
You can.
I guess the best way to go about it is just really to talk about so the interface of QMDB, just typical CRUD, create, read, update, and delete. And then it makes sense to start from what an update looks like. So you can in some sense, you can think of QMDB as you have sort of MMR, Merkle Mountain Range like structure, and then we layer on the mutability on top of that. So if we ignore the fact the exclusion proof, you just want to prove, for example, I have this value, this key value mapped to a key, and I want to prove that this version, right, of the value is the most current version. It hasn't been overwritten, at some point. So what we do here is we essentially have what's called an entry. So an entry succinctly describes the value for a particular key at a particular point in time. And it has abstractly a flag that tells you, this is the most current version. And when you want to overwrite it, you just have to set that flag to false and then write a new entry with the same key, a new value, and then the flag there is true. So you have to include that flag in the inclusion proof against the Merkle root. So that's at a very high level, sort of, for just inclusion proofs, how you would add a new entry, or rather overwrite a key in the address space.
Yep. Allow me. So I know there are common ways we're working on adding mutability to MRR storage as well, right? So there are many ways we can tackle this problem. But then, when we think about it, the desirable technical property is that to reduce the size of the proof. You can trivially add another layer of tree. Right? There are multiple ways you can add another tree to store the latest value version, right? Or you can do another route the LVMT, where every single entry on the Merkle Mountain range, you store the latest version, and you just have another MPT to store the version only. Right? And because the version only is also just increment by one every single time, and that is actually pretty cheap for a polynomial commitment point of view, because addition is way cheaper than multiplication. And that's how they handle it. But we decided to go another route, which is just very intuitive in hindsight from a system perspective, which is to coalesce them in a way that reduce the size of the proof, the hash that you need to do.
Yeah, I think we, you bring up a good point here. So I think this goes into some of the minutia around basically how you take a log and somehow say which entries are the ones that are actually active in that log. Because one of the big benefits, at least you called out in the QMDB paper, right, is because it's a proof, or basically the root is constructed additively over the entire log, you can prove the inclusion of any item in the entire history of the log, which if you, let's say you're trying to do some sort of historical proof, can be huge, right? Because normally with an MPT proof, you just have the state that's now, and then have some ability to kind of derive some sort of historical proof, which can be extremely expensive, which is why I think most chains don't even support historical witness proofs anymore. Or exactly. Most nodes, at least. But you bring it. Go ahead.
And that's actually a very interesting emerging property of QMDB, that you can prove any value that exists in any point in time in space, right? And we're still looking for a killer application, but one way that one example that we always talk about would be the T-WAP price. Right now, if you want to write T-WAP price into a contract, you need to add a lot of ad hoc storage to customize the logic there, right? But when QMDB, actually with the proper precompile, you can aggregate arbitrary price of arbitrary granularity at the tip of the blockchain without actually creating those storage. Right? And that's an emergent property that we can use.
Yeah, I feel like that's at least one place for basically coupling QMDB with some ZK style proofs can basically take what is a valid proof and then generate some arbitrary artifact from that.
So if the proofs can be derived, you don't need to store it, right? The storage is just sort of cache, right? It doesn't create more information fundamentally.
Yeah. I think so we got this log. It's got all this random stuff in it that, from time 0 to Fern. This is one of the QMDB, right, is as much as I'd love to say it's a silver bullet, one of the trade-offs you do make, right, is that the proof grows in size with the number of items added as updates because of this log. And so I don't know if you've thought about, kind of that trade-off here is is
that's
something's got to give somewhere, I guess. Maybe unless
that's a good question, right? But I would try to answer with a few different angles. First of all, we also have pruning and compaction, right? And after that, you can trivially just optimize it, like lower the tree again, and do some compaction, like it's just basic Merkle tree optimization technique, right? So it doesn't need to be a problem. And second, if you put it in a long enough horizon, assuming the ledger grows linearly or just super linear a little bit, right? And at that, let's say you grow to level height of 48 in 20 years. And after that, it actually grows really slowly. For you to go to one more level, you need another 20 years.
Yeah.
So the asymptotic cost is really nice. Like it doesn't really create any problem.
Because it grows log 2, I'm assuming.
Yeah.
Binary
So
tree
it's not a problem. Not to
we
mention
couldn't even get other data structure verifiable databases. I don't remember which one we tested to go as large as we went. At some point, they were breaking, right? That ours could just continue to grow. So in terms of scaling for large data sets, ours in our own tests, far surpass what was out there.
Let me put it out. I think the storage and the computing power grows way faster than log 2. So that's my bet.
So historically, that's a pretty good bet. Yeah. I mean, I
think it is more of a silver bullet, actually.
Sorry to offend. Yeah, I mean, I think So on the like the proof size component. So you mentioned that one cool trick of you can compress it. The idea there being that you basically take a root that's at some point, and then now you collapse that as to the start of the log, and then you kind of build again from that point in time. Or did you have something else in mind as kind of a way around that, assuming that you think some storage does not grow at better than log 2 rate over the next 20 years?
It's technically possible, right? So say that you have some QMDB at its core, we lay it out as a balanced binary tree, and then towards the left side of the tree, you have all of the older entries, which are temporally you've put it in earlier in time, and then towards the right side of the tree, you have fresher, newer entries. So at some point, right, especially if you have some compaction process to move sort of fragmented, non-overridden entries from the left side of the tree to the right side of the tree, you'll have an entire the entire left subtree of the Merkle tree will become stale, which means that if you don't care about proving the historical inclusion or historical exclusion, you can just discard that entire subtree, which means you can discard the root and then use the right half of the right child of the original root as the new root. But I think it's more reasonable just to leave the root as is. You can prune the storage if you want, right? But leave the provability. I mean, I think it's hard to say without saying this is the killer app for it, but I think it's a very powerful feature to leave the provability for all those historical entries.
Yeah. I mean, so we got a little diverged on the first thing, which was how do you get it to be current, right? So there's this term you guys include, twigs.
Yes.
Very nice play on the tree.
Let's talk a little bit
tree
twig.
theme. Yeah.
So in the when we were talking about proving inclusion, rather updating a value in a way that allows you to prove inclusion. Abstractly, there's a flag on every single entry that says this is the most current version of this particular key. The problem here is if you store this flag in the entry itself, in the leaf itself, then you actually need to update that leaf in the underlying storage when you invalidate it. So an update would take 2 writes. The first write is to change the original flag, the flag of the old entry, and the other one would be to write the new entry with the new active equals true flag. So to get around this problem, we have this idea of a twig, which is you take some number of leaves. In our current version, it's 2048 leaves. And you take the root of the subtree that includes all of those leaves, and you store the active bits or the flag, the set of flags, in a bitmap at the root of that twig, which means when you invalidate an entry, you don't necessarily have to overwrite that entry, but rather you just update a bit at the root of that twig,
which is in memory.
And what this really unlocks, right, is that by having 2048 leaves summarized by a single twig root, you can just store all of the twig roots in memory because it's 1/2048th of the entire world state size. And given the relative sizing of SSD versus DRAM, we think it's pretty reasonable to say that you'll have at least 1/2000th of your SSD size in DRAM where you can store all these twig roots.
And that's another hardware scaling law we are betting against.
Yes.
So it's pretty again.
Well, you're not even using SSDs mostly. You're using like NVMe drives for most of this research, right?
Yes.
Yeah. Yeah.
So, I mean, of course, if SSDs or your flash memory starts growing exponentially faster than DRAM, then we'll just change it to 4096 or whatever it needs to be.
I remember the funny story here is like when you guys were testing this before the paper was released. I remember I was talking to, I forgot his name, someone on the team who was like testing it on like a Raspberry Pi with like some NVMe drives hooked up to it, like some top shelf stuff you can't get on the cloud. And it was like, yeah, I mean, that's how you were optimizing. I was like, that's sick, because I think most people unfortunately don't go to that level of local testing to make sure it actually runs on like a local machine. That's like, oh, well, it ran in the EC2. Must be good.
We see a lot of like positive feedback from different teams reproducing the benchmark, right? Like there is a team that they're supposed to be doing their own custom database, and turns out their own performance on the biggest machine you can find on AWS is not even as good as the MacBook running the old version of QMDB. And they had to just chuck all the old work and just focus on this one.
I mean, in fairness, QMDB, I think we say in the paper, but I'll say it again, is 92% theoretical optimal. So there's not really much more you can do from here unless the hardware changes, right? As long as the hardware, the state of the art is what it is today, and then there's not a major advancement there. There's not much better you can do than what QMDB is. So it just makes sense that everybody uses it.
Maybe you should touch on that a bit of like what you mean by optimal there, like based on how many things you read, based on how many things you write to perform an operation. A bit more about it.
Yeah. In the paper, we talk about a disk I/O, right? Like, so the three characteristics would be a strictly one disk read per read, and it's amortize 01 sequential write. And for Merkleization, it's pure in memory, so it's 0 disk I/O for Merkleization. That's the overall characteristic. And if you think about the workload, right? If you look at the historical workload of Ethereum, is actually in most other like a real working system, only a small percentage. In the case of Ethereum, will be 10%, are the ones that create and delete, which incur a bit more cost into the QMDB, right? So specifically, the create and delete would create like a to read, because like how we arrange the key, like exclusion proof key, which we didn't talk about, but we'll talk about it later. Yeah. And it's 10% create double the workload. So then you can just do a rough math saying that you will have 90% optimal performance.
Yeah, I mean, I think it's always good to build into like some kind of like optimality bounds, because the worst thing when you build something you spend all this time doing it is someone's like, I found a better way. So same thing applies for like launching a project too. It's like if you base it on something that's pretty optimal, it's not like anyone's going to come by and do something that much better unless you really miss something.
It's kind of hard, like for a product system to have like a less than 1 disk read per read, unless you find any creative way to assume the workload like a locality, right? Yeah, but that's like an assumption. And often in blockchain, protecting the worst case is no less important than improving the average case. And you shouldn't have this kind of workload assumption, right? Which is dangerous. And really good like average case and worst case performance is also a very important part of the QMDB, because the tree, like you don't need to price the storage opcode with the worst case reaching the deepest part of the MBT. Like they're definitely the same, right?
Yep.
Yeah. So that's not a very good. Like, it's very predictable performance.
Yeah. To add on to that, QMDB does give up one thing, which is spatial locality. So if you have two keys that are spatially related, one is 0xA, one is 0xB. There's a high chance that depending on when you wrote them, they'll be located in completely different places in the log. But in the case of blockchain, right, you're really optimizing to make sure that the worst case is handled in a reasonable way. So you can't really assume spatial locality in a general blockchain application. Maybe it affects some very specific applications. But
And
Go ahead.
Yeah. So, in fact, like the way that people deal with these things is to if you look at Uniswap v3 EVM, right? Like they have tick. I think it's like a size of 7 or 9 bytes,
Yep.
and try to fit multiple ticks into a 32 bytes storage.
Mm.
And that's how they create like the spatial locality. And QMDB doesn't assume the size of the value, right? It could be up to
Yeah.
like 2 megabytes or something. Then the way you deal with it would be and you think about, let's say, Solana, right? You can have a 10 megabytes account, and
Yep.
you can fit as much spatial locality if you want in the bigger account. And that's how you handle it.
Yeah, I mean, I think there's like this. I've seen a lot of these like research papers come out lately of like, oh, we could change, ETH's gas target because like, oh, we did a run over like everything that's happened over the last 6 months, and so like this is safe because like it almost never happens. And I mean, like the thing that sometimes you need to think about is balancing that optimization frontier with the robustness of like what is actually required. Because as soon as you make that change, then that person that's been waiting to run that like deep storage attack can now do so. And I think even what was it, Base recently actually reduced their gas target because like it was getting spammed so hard with like state growth stuff. So like there's this funny project called like Zen, I think it is, where they like mine and fill like contract storage and then delete it as like a mining scheme. And like you look at most EVMs, like almost all the storage is Zen, like contract filled stuff, especially on Base. And so you gotta be careful.
Yeah, by the way, like as the whole space moving to ZK, right?
Yeah.
And the situation is actually worse, way worse, because ZK's attack surface is way wider.
Yeah.
Yeah, than system, right? So I would say in this regard, QMDB is again a silver bullet because it gives you a really good average case and worst case performance in authentication.
Rather, the average case is the worst case. The
Yeah,
worst case is
our
the
average case is the worst case. Yes.
I think one thing.
Yeah.
I think the other thing that's really nice that you mentioned is like it doesn't require like the Merkleization stuff is all in memory because you only need the most right-hand part of the tree to like actually add to the tree rather than like reading all over disk to like kind of fill it up. And yeah, I'm sure you guys came to this too, but in our implementation stuff, it's like, it's like 15 nodes tops and you like basically store it in memory because the depth of the tree isn't that big. So it's like you can just kind of keep going and not really have to worry about anything read-wise other than updating values maybe if you don't have them in memory. I think that's a good bridge into like, okay, so you got this log. We got these like twigs and stuff to give you like some current view of state. But like, I guess the question I think that probably ties it together for people is like, when I look up something in a database, it isn't by index, it is by key. So like, what is the mapping, I guess, or like, how do you think about the mapping from like, what is this like logical key to a position in the log? Because that's actually what you need for an application.
Yeah, so that's where the indexer comes in. We have like a separate in-memory indexer. I don't remember the exact numbers, but it's something like 15 bytes.
No, it's a way lower. I think it's like a 8 byte per entry now with more optimization.
We've been doing a lot of grinding behind the scenes to make this even more efficient, memory efficient, CPU efficient. So I guess it's now 8 bytes per entry in memory indexer. Yeah. And then you can look up the key in that in-memory index, and that will give you the offset into the log that you have to read from to get the actual underlying value. So decoupling, it's a really nice feature to really decouple the index from the underlying storage, because there are a lot of really clever optimizations you can do in the index, and really the index, the properties of the index, sort of the resource consumption and the performance is something that is unique based on what kind of project you're doing. So I think in the paper we presented 2 different indexers. One was like a full in-memory indexer, and then we also had like a what we call the hybrid indexer, that sort of has some on-disk overlay that increases the number of IOs that you have to do to look up a value, but it reduces the DRAM requirement by
just different space time trade-off.
Yeah. So like if it depends really on the requirements of your project, and there are also there's a ton of work. This is when the indexer is really it's a traditional key value store, and the space of academic research and also industry and actual industrial applications is really deep, spanning over decades. So you can leverage all of these optimizations for whatever specific use case you have.
Yeah, an interesting anecdotal case I want to share is that for the hybrid indexer, where you actually just flush down the B tree leaf on the disk. So every single read you incur one more disk read, right? So in theory, it would reduce the maximum throughput by half because you're doing 2 reads instead of 1, right?
Sure.
And when you benchmark it, you actually just halve the performance. So that shows you're really bottlenecked by the random read. And again, you don't need to run it. Just look at the hardware. You know how fast it can go.
I suppose for a bigger tree or a bigger database too, you could kind of, and if you're trying to be more cost effective, put this indexer in an NVMe space and then have the actual log maybe on an SSD or something like that as if you wanted to extend more than what RAM was able to offer you. Yeah.
There are many other flavors of indexer you can do for different trade-off. Yeah.
Okay, so we got the foundation there. It's we got this log. We're building a tree really over the log rather than a tree over the state, which to me is the logical leap. And then once you do that, there's a few new problems that show up, which is okay, if you have the log, how do you constrain it just to be able to prove what's current? How do you then look up keys and how they map to items in the log? Because you need that for the application. But something that you've touched on a few times now that we've danced around is how do you then prove that something isn't in the log?
Exactly.
Because that ends up being a huge thing for a lot of the applications that you guys I know are excited about.
Yeah. So as you mentioned, right. So for example, in EVM, you need to be able to prove that some key is not present in the address space. And just having the active bits or the flag, right, is insufficient to prove that. So we actually we essentially overlay a sparse address spatial data structure on top of what we've already talked about so far.
Yep.
And the way that we represent this is essentially a linked list. Say that you have 2 keys 0x1 and 0x4.
Yep.
0x1 will have some pointer to 0x4. So some sort of indication of what the next key lexicographically in the address space is. Which means that if you're able to prove, right, in the current state that your entry that contains 0x1 has a next lexicographical successor of 0x4, then you know that 0x2 and 0x3 don't exist in the current state. The consequence of this, though, as we touched on earlier, is that when you create a new key, for example, you have to not only write the new key, but you have to update its lexicographical predecessor so that its successor, right, points to the new entry that you just created. And likewise, for when you delete it, you have to update your lexicographical predecessor to point at your successor to remove yourself from the current state. So that's what we were talking about earlier with the 92% optimality. So depending on how you mix the creates and deletes into your workflow, those incur 1 extra disk write.
Yeah, can I add something?
And to be clear, that's an addition to the log with the rewrite. It's not changing it in place where you're not changing the log.
Yes.
Yeah, but that only occurs when you have a creation and deletion, which changes the key sequences, right? Which is 10% of the workload. And let me try to provide another a view on how to design that. So given the log database, right, the inherent properties that you can only do inclusion proof. So we're still just doing that. The real question, the real insight is how to reduce the exclusion proof to be an inclusion proof. Right. So, and the next question is how do you prove the key exclusion with just a key range? That's simple. There's no other logic around that. So we're not creating an exclusion proof on the log database. Not at all. We just use some trick to reduce the problem to that.
That's a great way to frame it. I hadn't thought about discussing it that way because you're basically just saying we're showing the thing before and after it and showing the inclusion of those. And from that data, you can then prove that there's
Yeah.
Exactly.
So we're aware of the inherent restriction of the log database, which is inclusion proof only, right? So that's just trim out whatever solution space you try to find. Just don't look in that way. There's no way to look in that way. So inherent.
Yeah, and this is something, at least with the ones we've been playing with, which we call like NEDBs, basically, is like we don't support this exclusion proof property because we don't have this like I guess like rewriting component of it. So I think it would be worthwhile to discuss why some applications need this exclusion proof, because it's like you obviously go through quite some length to like be able to provide this capability. It's one extra write per per creation or deletion. So like, what is the reason why someone needs this exclusion proof?
So concretely, specifically, let's say for EVM, right? When you're trying to prove, so they have a concept called zero value. If the storage doesn't exist, they will be initialized in the VM to be the default value, right? For all the integer value will be 0, for Boolean will be false, for example. So that's part of the VM machinery that you need to prove. But you take another step back, you always need to prove that to be able to really perform the state transition for arbitrary state that you need to prove, right? Like exists or not, even as simple as like if it exists, then do A. If it doesn't, do B, right? That's something you do. Yeah.
So it really has to do with like kind of this light client execution, or like witness style execution of a chain, or like a ZK.
Yes.
Like, well, I think the way I think about it is like you have state sync, and then you have more than state sync. And so state sync, you just need to know what's around. So you don't care if someone can prove to you what's not around if you can sufficiently and comprehensively prove what is around, which you have the root for. You can do a range proof over the entire history and get what is alive. The problem is that if you don't have the full state and you are trying to prove that some state transition function was accurate that initialized something, you can't prove that it didn't exist before that state transition function. You cannot prove that you initialized it safely, because you may have just excluded, not to overuse that word, excluded the proof that was required to do that. So in this world of like people moving to these like ZK driven execution models, like not being able to show exclusion means that you can't actually apply it in a safe way over this.
It's just like way less useful if you cannot prove exclusion.
I wouldn't say less useful, but I think it's less general, right? So if you can prove exclusion, you can implement basically anything you want on top of it.
Arbitrary storage.
I almost think it goes from, it's not less useful, it goes from not useful to useful. But depending on what you're trying to do. So very cool. So we got you did all this stuff from scratch, like built this all out in Rust, and I'll link in the notes too. It's a public repo you can play around with. So you went through all this stuff. So is it faster, and how much so compared to like other things? I saw this note that it's like 8x faster than the state of the art, and even 6x more updates per second than any key value database. So crazy idea here, right? Is like, you're Merkleizing stuff. How is it faster than a database that isn't Merkleizing stuff? So how do you think about that trade-off, or like what's going on here behind the scenes?
Oh yeah. So I think first of all, like our feature set. In terms of KV, it's a subset of the KV of the RocksDB, right? We don't have those kind of key iterations, so you don't have a lot of overhead maintaining those things. And second, even if you need to Merkleize, it's just mainly the cost of CPU, and you can pipeline it. Like you can basically hide it behind another pipeline, right? And third, QMDB itself is like sharded by key range, unlike RocksDB. Like you can build another layer on RocksDB to shard the RocksDB by key range, but there's another layer of complexity, another layer of like things could go wrong, right? But we enshrine that, so it's natively sharded by key, at the trade-off of not having so many rich KV features.
And also,
I think this seems to be a source of a lot of optimization lately in the space. Has been like turns out we just don't need this stuff with most things
Exactly.
provided out of the box. So let's just remove it. And it turns
Yeah,
out
yeah.
that
Turns
stuff
out
we didn't know
in-
we needed is actually like a shit ton of overhead.
Turns out in blockchain we happen to like hashing our key
Yeah.
all the time.
The spatial locality means nothing.
It doesn't mean anything to begin with.
Uniform workload is certainly a nice
Uniform
property to
workload.
have. Yeah.
I think what we have in the paper, we show some improvement in the performance of QMDB as compared to RocksDB. And that's really sort of attributed to the fact that RocksDB does a lot of work to perform compaction and keep everything in order for the spatial locality and of course for features like key iteration. But we drop those features and then you can get like a little performance boost.
Yeah.
I'm not sure how we got this far without mentioning it, but yeah, with compaction here, the compaction is not kind of like this like latent compaction that goes on typically in a key value database. It just doesn't happen here.
You mean like in QMDB, the compaction in QMDB?
So like for example, like if we go back to like the RocksDB case, like it's constantly moving stuff all over disk, this kind of compaction problem. With a log, depending on how you're doing it, you only need to rewrite on modification.
Exactly.
Or if you're pruning over like a sparse range. So maybe let's talk about a little bit of like, okay, so we got this database. It's pretty fast, even compared to KV, because we rip out features we don't need. It's pretty fast compared to other people doing MPT stuff because it's a totally different approach to it. And I think the last thing I really wanted to touch on here before we get into like the FAFO stuff is, well, what happens if the log just gets really sparse kind of at the front because you've updated most of the items, but not all of the items? And like, how do you prevent this world where the log just becomes the whole database all the time? Because you may end up having to store a bunch of stuff that's no longer active.
Storing what is the log? Yeah, so that's a detail that, I mean, of course, if something is no longer active and you don't want to keep it around, for example, if you don't want to allow people to ask you for the historical value, then you can just delete it from the log. You may run into some problems of fragmentation, like on the underlying flash itself.
Yep.
And if you want to deal with just that problem, you should probably just deal with that problem with some lower layer, some layer underneath QMDB. But QMDB also has sort of in what's the word for like in protocol compaction, if you so desire. So really, if you have, say, an entire left half of the QMDB Merkle tree as inactive, except for one entry, then perhaps it's worth it for your application to take that one entry and then essentially update that entry to the same value, and then put it at the head of the log, and then that way you can just sort of delete the entire left half of the tree, which is going to be some giant contiguous piece of storage on the SSD. That detail, I don't think we prescribe too much. We're not that opinionated.
I can talk a little bit more about it. So QMDB is actually like the compaction policy is pretty orthogonal to the QMDB thing, right? But if you want to constrain it in the context of blockchain, you want that policy to be deterministic at least. Right, and because there are multiple ways you can do it. Like you can have some simple system rule. As you're just building a layer one, like Solana, right? Ethereum. Then as long as the logic is deterministic, you can always reach the same outcome. But if you try to prove something like a ZK, then you want the compaction logic to be self-contained in the protocol. That's why we can store some metadata. Let's say how many percentage of active bits you want to keep in the latest state tree, right? And when it's loaded that, you just do some compaction, move some values around. And that would be self-contained, also deterministic. So there are different layers of implementation.
Yeah, the interesting thing here is the compaction actually changes the root. So like if you can't just like move stuff around on disk in the same way, like you can do other stuff, but like if you want to like compact the log, you have to rewrite it at the end of the log, which then changes the root. So like, the point around determinism is, well, do you want every node to have the same root, or do you want them to diverge? And the answer is you want them to have the same root. But one really nice property though of this like compaction is like you can charge people for how much they're compacted when you're compacting them. So like there are like interesting like tweaks you can add as you perform this deterministic compaction.
multiple ways.
One of the ideas that I liked, I'm not sure how much Raz and Isaac liked, was that we could incentivize people if they see some orphans way in the left side of the tree, then they can submit a transaction to compact it and then collect some sort of payout from the protocol for doing so.
Okay.
I think it's a little
That's-
too dreamable though.
You're trying to decentralize the garbage collection in that case. I'm not a big fan of that idea.
Well, another, I think, I don't know how big of a fan I am of that either, but I mean, like the other thing too is like what you can do, right? Is like if things are about to get compacted, you can actually even drop them out of the database and have them be like put in some like larger archival store where they need to be resurrected from like the previous MMR route because it's ever increasing. So like this is one use case I've always enjoyed about the MMR is like you don't actually need to do a lot of extra shit to recover things that you drop out of state if you never mark them as deleted, because you can then prove that they're recoverable if someone has that state at some point. So like I actually think about that as the most useful part of this like historical range is not the application side, but actually a way to like bound the size of the like the active state and then to be able to like bring stuff back in without actually having to incur any overhead on any of the nodes that are actually just holding the active state. So we'll see if that becomes useful or not. But I think this property being able to prove everything.
Tough high performance though, right? Like if you had to grab data that was on an archive node, that'd be tougher on the high performance side though.
So the trick is that the node itself would not do it. A user would submit a transaction that included a resurrection with a proof. Yeah. And so then you wouldn't actually have the high performance validator node actually touching anything old. It would just be like almost look like an insertion, but it would recover a key value. Yeah.
User requested.
I think there's like some sort of like kind of like state expiry thing that ETH had explored a while ago that like kind of could be adopted for something like this. The thing is with their approach, it's like got all these other trees, and what with QMDB or like kind of an MMR construction, you just get that out of the box from this like log construction. So
by the way, like if you want to talk about the system deterministic compaction, right? Like not in the ZK context, it's also the fastest way possible because you're just doing a lot of read, like a sequential read, and a lot of sequential write. These two operations are basically free.
There's all these crazy. I mean, this is the last thing we'll talk about on this, and I want to go into the paper you guys released here because we've spent a lot of time on this. But it's like there's also a lot of theory around like compaction strategy for the same reason why it's been studied for so long. And like one of the theories is actually don't use any heuristic and just compact the same amount of stuff that you write at the end, and you bound the amount of junk in the database. And that's the policy, for example, we use in our databases is like this sort of like just very stupid rewrite policy.
It's a great idea.
But there's obviously a lot smarter stuff you can do around like checking the quality of like the. Like
I actually like it, the stupid stuff. It's simple.
So, I mean, every year I'm trying to get stupider and stupider. It seems like there's better mechanisms that come out of just being increasingly dumb about it. So I'm a fan of that.
And one thing, like one very important property of QMDB we didn't talk about is it's ultra ZK friendly.
Oh, sure. Yes.
Yeah. And it comes in different properties. The first one will be you can create the block size, like an arbitrary block size, because you can Merkleize very fast right now, right? That's one thing. And second thing is that given like the size of the tree, how the shape, how it looks is very predictable. So to prove like inclusion, you're just doing the same thing again and again. Like you know how many hashes you need to do, and it's always binary tree. There's no rebalancing. There is no splitting node.
Yep.
It's like a very mechanical uniform stack you can build around that to prove something like that. And it's like that we're talking about could be 100x or 1000x difference compared to you needing to handle like how many compared to needing to handle the arbitrary shapes of the trees, arbitrary nodes and things.
Yeah. I mean, you guys explored this a bit in like that. I think it was called like the VApps, like kind of direction too. And I know this one isn't about that, but if you haven't taken a look at the VApps or the VApps paper,
another podcast.
Too many podcasts won't be able to code it all. So balancing. So we've now got this database. It does seemingly everything we want. You'd call it a silver bullet. I call it a pretty good database. And I mean, I think like the first paper or like the first section.
What's your bar for a great database?
I always like to keep that rung open just because we don't know what's coming down the pipe. But it's the best good database I know.
It's constrained by the number of electrons that you have.
Yeah. So I remember there's this line in this FAFO paper to give you some people that are listening some idea. And there's a line which basically says, without loss of generality, we assume that the underlying verifiable database is not a bottleneck of the system. So clearly the goal here was make the database faster than you could ever pack transactions and execute them, and then just optimize now this like parallel execution component. So is that maybe a good place to start here? So we've got this fancy database. It's verifiable, so we can add like all the ZK stuff to it and everything.
When we did QMDB and then realized, this unlocks 1 million TPS, how could we not do FAFO, right? How could we not do that next step and say? So it wasn't like our original intention was just let's just unblock this bottleneck,
Sure.
And then once we unblocked it, we're like, we got to take it to the next step. And so it was the next logical case. Like how could we not demonstrate the power of QMDB? And then it was just a matter of coming up with FAFO for scheduling and parallelism, right, of those transactions. So I think the bottlenecks, we got some point where I think the bottleneck could become QMDB again, right, because of the scheduling. So, let's dive into it.
Yeah, so I mean, I guess the way to think about that is like you have this database, it runs at this speed, and you mentioned that, well, there's a bottleneck here. So I'm assuming you tried it without like FAFO stuff and it just did not hit your target for throughput because otherwise you wouldn't have written this whole thing. So I don't know if you can share at all about like that journey of discovery of like, I'm assuming you had QMDB and you're like, well, how much can we execute? What happened from then to like having this like FAFO paper?
Yeah. So, okay. To share that journey, I need to take another step back to think about like we always think about in terms of like a bandwidth, right? It actually ties to the very first question of the podcast, like why are we starting from database, and answer like without the loss of generality, we assume there's not a problem. So we would like to think about the system with a bottom-up perspective, like create infinite bandwidth of the lowest bottom layer and build layers and layers on top, right? And that's how we got started with the database. And when we after that we go into, so think about blockchain, a decentralized database, just no more than a database with a virtual machine on top, right?
Sure.
And let's try to add the virtual machine on top this time. And we first started to run it sequentially, and it stops at like maybe 15,000 TPS. That's like how fast the interpreter of EVM can go. But like it's actually quite decent. So EVM is not slow as people think, right? You can add a lot more fancy trick like a just-in-time compilation to handle bytecode things, but it's actually not that necessary. All you need is just a way to extract more parallelism of the workload, right? And how to do it. If you look at just like intro block, the things of the same block, there are very limited things you can do. You can have something like a block STM to continually resolve the conflict as you settle, right? But if you take another step back, imagine the situation of a really high throughput blockchain, right? Where you still have the time to inspect your mempool and extract the block with the highest level of, I wouldn't say highest level of parallelism, but pretty good level of parallelism within your computation bound, right? And that's how we look at it. And we try with different workload, different algorithms, and step by step, like any other system optimization, and then you eventually hit 1 million TPS. Yeah.
Just like that.
Just like that, Okay, so in fact, there are more details to it. Right? So if like a EVM can run 15,000 TPS, so you at least need 70 cores to hit 1 million, right? At least.
Sure.
Okay, and there is like a 96 core machine on AWS Then now let's think about how to use the RD20 cores, because you still need to maintain the QMDB, QMDB, right? Okay, then what's left for the scheduling algorithm and the simulation and things, right? So the space just gets smaller and smaller, and you need to be even more creative over time to handle the problems, right?
And the thing that obviously comes up there is when you have many cores, how do you avoid bottlenecking on like a synchronization issue between those cores, right? Yeah, fun times.
Synchronization,
yeah. We'll go into this shortly, but I wanted to ask one quick question here, which is like, this paper certainly implies you believe not having developers or users like specify read or write dependencies ahead of time is the right approach. Maybe you can talk a little bit about that before we go into actually trying to.
I can go for an hour on this.
Someone can listen to this podcast at 3x speed, so you're good to go as long as you want to.
I know, like basically the static analysis approach, right? Like it's how Sui and Zhang go design their VM these days, and it's great if you don't want more flexible behaviors. Because the concept that we talk about again in the teams, like a leakage. So if you ask the user to specify the load and store, basically, right, of the thing you're going to call, you cannot call into multiple layers deep because you don't know what's going on after multiple layers. Now you're leaking the memory layout of applications into the user, at least to the developer, right? Then you cannot do anything dynamic for sure. So we are a big fans of not doing it. But try to do it in a creative way where you can just do some simulations. And
someone I was talking to had a really interesting take on this, which was, I think it was just to give credit where it's due, Henry de Valence or Georgios, I was having a conversation with him, and they were like, most early actual like programs, way back when, before like processors were super smart, there were like some approaches which had like basically the developer specify like exactly how to use the processor and like exactly how to use these instructions. And because of that, it gave no freedom of movement to like the compiler to be smarter than you on like how it could sequence things and like how you could interleave things in a creative way. And only when application developers were stripped of their ability to be so smart did it actually get really fast. And so the question that has always come up to me is like how you retain reliability in like a Byzantine model in both cases, because they both have issues with like how all these dependencies are pulled, to keep it fast without basically opening up a massive hole for someone smart to like kind of play these games in a parallel world, right? Because like, just to be clear, the static dependency model is really easy to fuck with. Like you can just have every transaction you send touch the hottest slot on the whole chain and then break the whole parallelism. So it's not like that's some silver bullet either. Like you can just absolutely clog up an Oracle or like do anything like that. So it's an interesting.
Actually, you don't even need to be Byzantine for that, right? All you need to do is want to trade the most popular meme coin on Solana.
Fair enough. Yeah, I mean every pool is technically an Oracle, right? So yeah, I mean it opens up all these interesting questions around that. So we'll get to that, but like let's first talk about a bit around like how this new construction you have for packing things is interesting. Because I mean, I think before we get started, right, the idea is the whole name says it all, which is fast ahead of formation optimization. So you're
just say the word. It's fine. Just say the
word. FAFO. Yeah. I'm assuming that has something to do with fuck around and find out, but I'm not going to speculate. So maybe you want to, let's start from there. There's 4 components: parallelize, paraframer, parascheduler, and then the block formation component. So maybe let's just start off the problem from scratch, which is like we got transactions coming into the mempool. Now what?
Yeah, so I think the overarching idea is really, and you touched on the problem, which is coordination between cores. The solution that we are using here can almost be boiled down to just OCC. So we're optimistically, pre-computing what we think your transaction will touch as far as stores and loads. And under that assumption, we build something that is highly parallelizable, or at least we believe is highly parallelizable. And if it happens to be that some state change caused that transaction to not actually touch the stores and loads that it was analyzed to do at the beginning, then we just put it back to the beginning of the queue and then try again. And then the hope here is that we optimize everything to be super tight so that first, this is unlikely to happen. And if it does happen, the experience is not too bad. It'll get pushed through the pipeline very quickly at high throughput and low latency. So with that out of the way, maybe we can talk a little bit about the individual components. And we can start with parallelize. So parallelize is basically the first step of the process. So either the user, right, or the developer will provide you a static access list, or we'll just run the transaction, through a simulator and then see what pieces of memory, what pieces of storage it touches or it doesn't touch.
Yep.
And this here, the optimistic part is we have some initial state, and then we run a bunch of transactions out of the mempool in parallel against that initial state. So you introduce a little bit of inaccuracy, but this is basically infinitely shardable. So you can chart across multiple cores. You can even chart across multiple machines. So you can have a bunch of participants sort of collaboratively trying to analyze all the transactions in the mempool. So the output of this, right, output of parallelize is going to be some set of transactions. Each of these will be annotated with the set of stores and loads they'll do. That goes into the paraframer, which is the next part of the pipeline. And here, I want to shout out to another researcher on our team, Kelvin. He's thought of a lot of, invented many of the mechanisms that we used both in QMDB and FAFO. And one of the things he invented was the parabloom filter. So the parabloom filter is basically going to be it's a bloom filter with some some false detection rate, and you will have each of these bloom filters represent the aggregate read set and the aggregate write set of some bundle of transactions. So you're basically very, very efficiently and very concisely representing all of the stores and loads of many transactions in one tiny bloom filter. And all the transactions that don't conflict with any of the other stores and loads in that bloom filter can be put into that bloom filter, and then everything represented by the bloom filter can be run in parallel.
Can I add something to it? So the parallel in the bloom filter has several layers of meanings, right? So the first thing would be things coming out of the bloom filter can be run in parallel, right? But another very interesting design in that is the parallelization is not just multiple core, but across the bit of a 64 bits word size of the CPU. So we use the bloom filter to parallel schedule 64 groups with 1 bit each. That's how you can schedule that fast.
So I remember when I saw this for the first time, I sent some questions over around most people just use a map to kind of track the keys that are being touched. I think even Solana or some other people kind of use that because you assume hash map pretty fast in memory. And I think someone on the team was like, actually, this is way faster. So it turns out small bloom filters with bitwise checks are much faster than hash map.
Turns out. So
I mean, the whole reason that we have to do
that's how the million just shows up.
We only have so many cores on a single machine, so we can't really afford to spend a lot of resources. At some point, we actually did an analysis of we have this many cycles per transaction to detect the conflicts, right, and then schedule it. So how do we chop up 3,000 cycles into little units of computation?
Wow.
So one of the it's actually a very important trick that we use is the parabloom actually fits in exactly half of the L1 cache. So you don't have any sort of latency when you're trying to fetch from the lower level caches or even from main memory.
Sick.
So the next piece of that, right, paraframer in the paper, it's not as involved as parabloom. Really, it's just a little wrapper that defines a policy by which you eject frames from the set of 64 frames. Then after you've ejected those frames, right, then that sort of forms a transaction stream. So you take frame by frame, and then you just order the transactions within the frame according to some arbitrary policy. And then that goes to parascheduler. So perhaps one of the parts that may be hard to understand in the paper is why did we take all this work we've done to the frames and then just collapse it into a flat stream, just to, again, in parascheduler, repack it into the exact same frames. So part of the reason we can do this is because Parabloom is so incredibly efficient. And this really simplifies the overall implementation architecture. And what this actually allows you to do is, like, say you have one block builder or proposer that's really packing this transaction stream, then you can stream that sort of live. You don't have to pack a block. You just pack a flat stream of transactions. It's all the other full nodes, all the other validators, and then they can just perform the same super efficient logic to reproduce the same frames. And then you sort of, it's like encoding the frame information in 0 bits, because you just replicate the logic on the other side.
Sure.
And then the last step
The
here,
order basically is being that the ordering of the transactions themselves is the encoding. Basically, because it's reproducibly derivable.
Yeah. So a combination of the ordering plus the policy by which you pack the frames. And then the last step here, we have the parascheduler. Is what it does is it precisely calculates, right, what are the data dependencies and how fast can we dispatch each of these transactions without creating a data conflict. So this extracts, for example, the Parabloom is not 100% accurate because it's a Bloom filter, probabilistic data structure. Parascheduler turns that into a deterministic. You are getting the absolute maximum amount of parallelism that is possible out of this transaction stream. And in the end, if your blockchain needs blocks, some blockchains needs blocks, then you can just insert at arbitrary boundaries. So I've decided that this set of transactions is a block. So I'll put in a block header here, and then do with it what you will.
And so the basically in this like para framer, and the reason why the parascheduler has to re-execute anyways is that when it actually executes, the read and write dependencies may differ from like what was actually simulated earlier. So what happens when that happens? I'm assuming you mentioned, I think alluded to, that the transaction is recovered.
So exactly what you do there is not something that we have a very strong opinion. You must do it this way, but I think the way that we implement it right now, which is a detail not exactly represented in the paper, is it goes into a separate priority queue to be reanalyzed and retried at lower latency. But there's no hard technical reason to do that. It's mostly like a UX kind of thing.
It actually it is a little bit related to the now like a Byzantine workload. Something related, right? But I just want to lay down the fact, which is like let's say you have a Uniswap pool, right? And in the pool, every single transaction has to be run sequentially. Even with that workload, FAFO is able to execute that pool at 10,000 TPS in parallel with other things. And the proper way to counter those things would actually to have a policy to schedule these things as a part of the frame, like from time to time, just spread them out.
Well, so that was my follow-up, is like, if you're trying to minimize conflicts in like the transaction stream, like there's this question that comes up of fairness, which is like, if you're touching things that are popular, it almost seems like you'll have less popular stuff in the stream because it may have a higher conflict likelihood. So like, I'm curious how you think about that. Like, I mean, obviously with the simple payments case, like this is great. But the question is like, if you have like spiky popularity, what do you think?
So go ahead.
Okay, so go back to the fundamental again. If you have strictly sequential workload, there's nothing we can do, right? And then we can tackle it with multiple layers. One would be, because like first of all, these things are agnostic to VM, right? On the VM, you should be able to add a lot of like atomic like data structure. Like you can find that on Aptos. You can find that on any other VM, many other VMs, right? To encourage the people to create like a more parallelizable workload. And second, you can also make the workload more collision price aware. And that's some like other policy you can add on it based on their characteristic of your VM. I think that's the general idea.
Also, like there's a ceiling for obviously how much a single application or a piece of memory can be touched, but it means that other applications won't be affected by that application experiencing a slowdown, right? And so in a world where everything is using this, right, and this is like a universal where tons of different applications exist, right? They're not hurting each other, which you see on other blockchains where meme coin drops and everybody on the chain feels it. This would not happen, right? Only that application would feel it.
So it's
everything
like
else would be ripping.
Pros and cons of fairness, I guess.
Let me put
fair
it
to
on.
who?
So, is it fair to the CPU, right? So let me put it the other way. FAFO would not perform worse than any other system in terms of this kind of high contention workload that you have to execute sequentially. Yeah.
So I guess it becomes this thing where like the fee, it's like a fee rate given your parallelism is kind of high, like given your conflict rate, because like even if you have like a super high fee, like you can kind of go ahead of it, but like to get in, the required fee may actually be lower based on what state you might be touching, depending on how that. Obviously, this is all a VM concern.
We didn't go too deep.
If you take another level, like more abstract, right? It's still the resource allocation problem. I think it will be most effectively solved by the market if you cannot transparently solve it with just machine, right? So it's like we are at this point where you have to solve it with other combinatorial approaches more than just the computer.
So I guess like this is I think like an interesting construction in isolation. I'm curious how you think about how you would actually integrate it into a network. Like are like full nodes or like some leader or like some dedicated sequencer sending this stream of frames?
FAFO itself, like it's clearly more of like a sequencer thing where I can is in charge of everything that's come. The sequencer is in charge of everything that's coming in and can try to fit as much as it can into a block, right? Obviously, it doesn't think about MEV or any of the other things that come into place and how a sequencer thinks about it. It's purely kind of just showing you what the bounds are, right? Like what you can actually do on a single machine, what is possible, right? In practice, obviously, I think FAFO or how we demonstrate it is not really applicable to like super decentralized things like Ethereum, but layer 2s and VAPs and things like that can still be very applicable.
Because I guess my question was like, like one of my things was, well, could someone mess with this stream? Like, how could you know that like the stream had certain properties about it? You really can't because it's not like a globally optimal stream. It's like what you know at that time, let's
say like we can lay down some ground rules there. So the blockchain's transactions has to be serialized at the end, right? And that's your interface talking to different parties. So given any like agree upon policy and then a scheduler, scheduler. Even if you like stream it in stream the transaction in serialized manner, right? All the node will still be able to reconstruct it and don't need to go through the planning stage. You can execute it, given that thing. So you actually reduce the load on the full node.
Sure. And I guess the other thing that's like the idea here is that although there are other constructions like a block STM or like some of the other things that do like OSCC style or like approaches here, that there's a lot of benefit to doing it first and then doing it again rather than kind of like doing it just that one time during execution, because there's a lot of overhead of like actually if you get like a shitty stream, it's kind of like, well, it could be pretty gnarly in the STM workload.
By the way, like if you want, you can also interleave the block STM into the downstream of the parallel scheduler. You just keep resolving it until it's done. Just don't put them back to the main pool. And still another slot time, right, to handle it. If that's the preferred policy.
Oh, that's an interesting approach. Yeah, like you could just avoid that fallout, and then maybe track if there's certain patterns that.
Yeah, or you can, let's say you got 64 core. You can allocate 2 core to resolve these things all the time. a lot of things you can play around with it. And
yeah. I mean, I think it's interesting. So like this, you mentioned is now open source as well. How does the performance look? I mean, it sounds probably pretty good. So you hit 1 million TPS.
Yeah,
you compare against some other stuff. What are those things you compare against, or like kind of what are those things you think about that like really affect its performance?
Maybe Raz, you can chime in.
Yeah, I mean, so we compared against like Aptos did the Chardines part, but their bottleneck was database, right? It's like we had like an unfair advantage with QMDB. So we, it's hard to compare against anybody who's trying to do this because they don't have the silver bullet or the good database to work with, right? So they're working within the bounds of their constraints there, and they did an exceptional job, right? The app Chardines had, I think it was they were hitting 33,000 TPS or something per data cluster of all these different nodes. And what we wanted to demonstrate is that you could, with that database, you can achieve that on a single device, a single node. And so I think, and to even make it more, to show more of an impact, more of a mic drop, we did on Ethereum, an EVM, right? And we wanted to show not only that EVM, that we love EVM, we think that it is not slow, but not only that, but that it can achieve be as faster than anything out there, right? With the right setup. And so I think it's unfair to compare it to that just because we have the other part with the database. But it's just shout out to their work because they were able to do it as well. And it's cool to see that. And so it's cool to see the space move towards high performance and trying to achieve with the high performance, we wanted to achieve more decentralization as well. So I don't know. Talk more about that other stuff.
We actually, like, if you want to run more complicated workload, like we're using ERC20, right, as a test bed. The EVM interpreter does impose some like a scaling limitation, but we also have a very cool in-house solution that is not open source yet, which is like a just-in-time compilation for the bytecode that could take it further. Like if we want to play with it, like it can go further.
Future research. We don't usually talk about future research.
I was gonna say I was gonna ask a question like that,
but I would say like the overall taste, like we have a very strong contrarian view, if you may say, is that we want to scale the performance not with more money, more machine clusters of them, but with actually simplicity. If you look at the open source code base of FAFO and QMDB, the line of code is actually surprisingly small. Because it's simple, right? Because simple. And that's also part of why it is fast.
I think one of my favorite quotes is like, if I had more time, I'd make it shorter, or like make it simpler.
Love that one.
And I think of a lot of this research over the decade here since Bitcoin, like as just like how can we make all of this much simpler, and as a result, seemingly much faster. So
that's our engineering principles, is always to try, like, we're always trying to strip things down to what is necessary and have nothing extra, right? And like the common theme of all the things we keep putting out with QMDB and FAFO is we build around like the underlying hardware, right? Like the L1 cache of the CPU for FAFO, so that we can get that speed gain, and the SSD and the write, and eliminating that write amplification for QMDB. Like realizing that we don't have to fight against the hardware, we can actually build to be optimized for it, and get them let the hardware do the work, versus us trying to be cute with some clever algorithms.
I like it. It's how we kind of go about it too here. I think someone listening to this podcast is probably like, this. You can go pretty deep into all of these different things, and I'm curious if you guys, as you've like gone through this trajectory of like going from really just having an application all the way down into like the deeper and deeper areas of the stack. I mean, you guys have all been at LayerZero and LayerZero research for quite some time. I'm curious if you have any tips for like people that are trying to get deeper into this stuff. Like, is there anything that you remember that really helped you get deeper into it, or like really helped you explore like some of these like lower level optimization components that someone that's like, I don't really know where to start, might want to dig in, particularly on like the storage side or on the execution side of things?
I think the view mode is actually my gateway to this rabbit hole. Yeah, the hyper SDK, and then
Sweet.
unfortunately, I think in the space of blockchain research, there are not enough reproducible data sets, not enough like a well standardized benchmark. So I guess all you can do is really go from the first principle. Sounds like a big.
Yeah, and we're fortunate at LayerZero then that we get to put an endpoint on every single blockchain. So we spend a lot of time working with those teams and understanding why they built things the way they built them, right? From Ton to Solana to Aptos, everywhere, right? We're looking at that, and because we have this advantage of being able to see, like every kind is in their own ecosystem, focusing on the thing they're building and not necessarily seeing the whole what everybody else is doing, and we get this broad view of what is being built and the approaches that are being taken, and then we can kind of we have advantage of being like, oh, like, well, this is a good approach, but I wish they'd taken this from this other team, they could build this, right? And so it allows us to take that knowledge, institutional knowledge we built within LayerZero, and put out really compelling research to help everyone.
Classic case of the not built here technique, which is not really working. I actually had a very similar experience when I was at Coinbase, working with all these different integrations, because I could see just how differently different teams were approaching the problem. And I also lost a few holidays to trying to keep certain nodes up because they did not learn some important lessons, but we'll keep that there. So yeah, I mean, it's an interesting approach, because I mean, I don't know, you see a lot of people that see these things and they're like, well, how come the blockchain I'm using is way worse than this as well? And it's like, I see, I mean, the TPS number is a classic one. And so I'm curious, like, as you think about through this research, you touched on this a little bit at the beginning, but is there like some goal you'd like to see, like kind of a lot of this research be used? I'm assuming like in different chains to like really take it to another level, or is your door open if people are like interested in applying it to what they're building to come and ask you about it? Or I'm curious how you want to see these ideas get out of the classroom, I guess.
So we put it all right. We open source everything. We make it like, we're not trying to limit people from using that research. We try to put everything out there, and happy to answer questions. The teams reach out to us all the time. I think you're going to start seeing QMDB and major L1s and L2s over the next few years. I think it's a big change for a lot of them. So it takes time to do that, but I think it's a worthwhile investment, and that like whether we wanted to or not have it happen, it's going to happen because it's just it is the best approach. And we want to keep putting out the best research that impacts the space, and for it to impact the space, people actually have to use it. So we want it to be used, and we want to move the direction of crypto towards being ultra decentralized, right? And the founding principles of us, like I said at the beginning, is permissionless, censorship resistant, immutable, and we want that kind of mentality in all blockchains that are out there. And so if we can put tech out there that moves in that direction, then we're doing our part to have a future that we want LayerZeros to exist in, and everything we build in to exist.
I think that's a great way to wrap it up here. So, you guys have been super generous with your time, going super deep, up, deep again, back up, and yeah, I mean, it's been awesome to chat about this, and I'll link obviously all the work you guys have been doing. But before we wrap up, I don't know if there's any final thoughts like you guys want to share on like either updates on like how things have evolved since you released anything, or like kind of what you Isaac already gave him a small hint there of like maybe things may go, but I don't know if there's any final words you want to leave anyone listening to this with.
I think Raz, you can.
No, I mean, we're not done putting out research. This is a core part of our LayerZero team. Like we have 11 researchers on this team, and we will continue to be moving the space in the right direction and help guide it through great technical innovations that will come out of this research team and LayerZero.
Cool. Alrighty. Well, thank you all for taking the time here, and really enjoyed chatting about this. And fun part of all this being open with all the papers is go run it yourself, see how it runs, and if you run into any issues, you know where to reach out. So, thanks again for the time, and talk to you guys later.
Great.
Thanks.